Hello there, this is exercise 17 for year 13 maths. We saw a lot of work on the normal distribution in year 12. Unlike some other groups from other colleges, we did it early in year 13, so it was a bit easier for us. But we're going to try and make sure we understand what's going on in this normal distribution and remind ourselves of some of the things we've done in the past, I suppose. A few things to remind ourselves of, first of all. If we're going to think of something as being normal, there are certain considerations to make, and I'll go through these. The first one is it should be a symmetrical curve. You saw that at the beginning. We had a curve which looked roughly like this, and this is the standard shape for a normal distribution, and it's usually symmetrical about some mean. And the mean, you remember, is written with this symbol mu. So it should be roughly symmetrical either side of it. It should only have one mode, so if it looks, I don't know, some distributions go up and then they kind of go up and down like that. That can't be normal straight away because it can only have this one mode. Sometimes this is called a bell shape. You might have seen pictures of old bells in old churches, and that's not dissimilar to that shape. And thirdly, well, I've split this into three parts. Almost all the data will lie within 3 standard deviations from the mean. So by the time this basically hits the bottom, and you don't get any more values, and this basically hits the bottom, you can split this into 3 standard deviations on either side. And we actually saw this in the initial picture. Look at this. Up to 3 standard deviations is at the point at which you run out of numbers. There's no more numbers beyond that point. So we have that one rule. So this is, if you like, whatever the mu is. So let's imagine my mu equals 40 for the sake of argument. I'm expecting on average to get 40, and my standard deviation, I'm told, is 5. So this would be 40 in the middle, and this would be 45. This would be 50. By the time we get to 55, we basically run out of all values that I would expect to get from this: 35, 30, and 25. And by the time I get down to 25, I'd run out of all numbers. So basically, in that example, I'd expect this. I would be very surprised if I got a number from my data, say at 60 or 70. I expect everything to run from 25 to 55. Very surprising to get anything beyond those limits, if it's normal. 95% of the data should lie within 2 standard deviations from the mean. Well, that's basically from here to here, and we could say that in between that we'd expect to get 95% of all the numbers. And the third and final one is that we expect roughly 2/3 to be within 1 standard deviation. So from here to here, it's actually something like 66%. You can see that's close to 2/3. So this middle section is roughly 2/3, and you can see the height of it. You get lots of numbers around the middle, and fewer on either side. So we've got this rule then about normal distributions being of a certain shape, and we're going to need to do a few examples. So my first one is I've just drawn a couple of graphs, and I suppose I want to know is, are they normal distributions? And in actual fact, it gives the game away in the question. It says explain why the normal distribution is not a good model. Not a good model. And look, 2 reasons straight away. I'm looking here. Look at that. It goes up, it then seems to come down, and then seems to go up, then it goes down. So we describe this as being bimodal. Therefore, it can't be. It's not normal. So straight away, bimodal. It goes up, down, up, down. It can't be normal. Well, this one's not bimodal, but you can definitely see it skewed to one side. There are more numbers on the right. We call this actually negative skew. The tail is over to the left hand side. The high part's on the right. That's negative skew when it's over to the right, and when it's not symmetrical, I suppose. So not symmetrical, and one of our rules was that they must be symmetrical. So therefore, not normal. So I found 2 examples which aren't normal, bimodal and not symmetrical. What about ones which are? In a sample, it is found that the mean time taken to complete a puzzle is 42 seconds. Right, and so let's just write it down. Mu equals 42. I'm using the proper symbol for this. With a standard deviation of 28. Standard deviation, sigma is 28. Explain why the normal distribution would not be appropriate. Well, alright. So, there's another example where they're saying it's not appropriate. Well, let's just use our brain. 42. Now, we do have a rule that says all values within 3 standard deviations. So, for instance, if I was to do 3 times 28, I get 84. So if I was to add 84 on, that's basically telling me it's going to get down to the bottom at 42 plus 84, which is 126. I would expect everyone to have finished the puzzle after 126 seconds. But if you go down to the other end and say, when do they all finish? Will anyone... Well, 42, if I take away 84, I get minus 42. Fluke of the numbers, I suppose, but minus 42. And look, it's impossible to do the puzzle in minus 42 seconds. You know, 0 is obviously around here somewhere. So in real numbers, in proper life, real data, this lot effectively is impossible to do. And therefore it's not normal. For that reason, I would say. Let's see what the answer says. 126 minus 4. Yeah, negative times, so it's inappropriate to use this data with the normal distribution. So, new question. We've got, it says the maximum temperatures recorded during each month in Cambridge are known to be normally distributed. The data for 2005 are given below. Okay, then, so we've got these numbers. What does it want us to do? Calculate estimates of the mean. Okay, so we can easily type those into a calculator. So I'm going to quickly do it actually. So menu 6 and 1 variable, and I'm going to type those numbers in. I could use the actual formula since they've given it, but it's probably easier just to type them in. Hopefully I don't make any mistakes. Hope you're doing the same thing. Hope you're typing them in as well. Pause the video if you are slightly slower than me or slightly quicker than me. I apologise. So I've got them all in. Hopefully there's no mistakes. I'm going to quickly check them now. Then I can press the option button, 1 variable statistics, and I get these numbers. So who knows if they're right or wrong. I get the mean, x bar, which of course is an approximation for what it should be. How good it is, really, I suppose it's only good as the sample itself, 15.05. And the standard deviation, sigma x, is I get 5.6, well 5.70, I suppose. Now I've got those. It says, now remember it's normally distributed. So I have got this rule. You might remember this rule. Outliers are beyond the 2 standard deviations rule. And we talk about it being 95% of the data within 2 standard deviations. So if I take my mean, now really what I'm doing is I'm saying, well, let's assume my mean is 15.0. Let's do that and let's pretend it's 15.0. Was it exactly 15.05? If it was, I suppose that's why I did it. So I'll leave it at 15.05 then. And the standard deviation, well, again, is this a good estimate of my standard deviation? Again, that's arguable, but we're going to have to use it, so I'm going to write 5.70. And if I times that by 2, I get 2 standard deviations, and 2 standard deviations then are 11.4. Now, I can then take my 15.05 and I can add 11.4 onto it. That gives me my top number that I expect all my numbers to be between 26.45. And if I do 15.05 minus 11.4, I'll just do that on my calculator, I don't want to make a daft mistake. 15.05 minus 11.4 is 3.65. So basically all my numbers should lie between these 2 values. Now, are there any outliers? Were any numbers below 3.65? There's no numbers below that. Are there any numbers above 26.45? Just looking. No. So all numbers between 3.65 and 26.45, therefore no outliers. No, well, none that we know of anyway. It's as good as we can get. It's only meant to be an estimate, so that's question done. When n is large, now look, this is a good example. This isn't a binomial distribution, but it turns out if n is big enough, then the distributions look more and more normal. In fact, the greater the value of n, the more normal a binomial distribution looks. We can use this fact to approximate normal distribution, or using normal distribution to approximate binomial distributions. And when we're allowed to do it, well, there are certain rules. One of them is basically, is n large enough? And we can tell that. We can look for np being bigger than 5, or n1 minus p being greater than 5 as well. These two things are meant to be true. I suspect for normal A-level maths, it's good enough to say, is n big? Is if it's a big number, we can probably do it. So here's an example. The spinner is spun. The probability of landing on green, well, either lands on green or it doesn't land on green, I suppose, is the basic argument. And the probability of landing on this area is 0.4. And we can use our binomial distribution button to work out this probability. It's saying I'm going to spin it 100 times. Well, I think that's a big number, by the way. But if I spin it 100 times, I'm going to go menu 7. And on menu 7, I've got binomial CD. So I have to press the down button, and then I press 1, binomial CD. And it says list of variable. I always pick variable number 2. So what's my x? My x value here, I'm going to just write it down. X is 45. So I type that in. My n, well, I'm doing that 100 times. I'm spinning this spinner 100 times, so I'm going to type 100 in. And what's my probability of getting the green? It's 0.4. So I'll type that in 0.4. And it tells me what this probability is. I could work it out properly, but this is a much easier way of doing it. Probability x is less than 45, or equal to 45, is 0.869. Now, what I want to show you is you can do it by using the normal distribution instead. Now, mu equals np. That's basically how many times I expect it to happen. Mu is 100 times by p, which is 0.4, which you can work out easy enough to be 40. Sigma squared, our variance, is np 1 minus p. Well, we've already got np, that's 40, times by 1 minus p is 0.6. Well, that's 24. So we're really saying we've got a normal distribution. We can say we can approximate x using a normal distribution of mu, which is 40, comma 24. Now remember, that's the variance. That is sigma squared. And what it allows me to do then is to work out a normal distribution. Rather than it being binomial, I can say it's normal. So there's my 40. And I can find, using this, the probability that x is less than or equal to 45. Now, it's slightly dodgy. You'll soon realize what I mean by that. Well, maybe further mathematicians might. So I'm going to now press menu 7, and I'm going to go normal CD this time. The lower number, well, our lower number, we want less than or equal to 45. 45 is there. The lower number is up here. It's meant to be negative infinity. I always type minus 9999 in. My upper number is 45. My sigma, what was my sigma? I worked it out. It's root 24. And my mu is 40. And that gives me an answer. It's 0.846. And the idea of this is that answer is quite close to this answer. Explain the main differences. I'll do that on the next slide. So 0.846, 0.869, we've got all of that. Everything is right. The main difference between the two, of course, is the binomial is what we'd call discrete distribution. Only certain values are possible. Whereas a normal, we pretend, in our example here, but a normal distribution implies that all values are possible. In reality, that's not true, but that's only meant to be a rough approximation. But I've run out of time. In class, we're going to do exercise 17E, questions 1 to 5, it seems. and we can obviously do a few examples to remind you of a bit more. Best of luck.